Welcome back. Now that we've turned up the volume on these calculus questions, I'm in the volume packet, middle of page 7. I just wanted to make sure before we left the day we got a chance to practice a couple more times with finding this volume. So example 2 says you have the sketches. Here's your 2D version of the sketch where you're taking the graph of y equals the square root of sine of x from 0 to pi, and you're going to spin it around another horizontal axis of revolution, the x-axis, to get this 3D maybe football or rugby ball shape, which has, if you took that rectangular kind of region here and you spun it, it would give you this circular disc that's upright. And you're practicing integrating from 0 all the way to pi, the areas of all those discs as you travel along the shape. Well, let's try to set this up the same way we did the last one. So here is just a sketch of one disc, right? And you have this variable radius. I've been calling it capital R. And the radius is the distance from the x-axis up to this curve. And this curve is y equals the square root of sine of x. So that's the height of that is actually what we're going to use for our radius of each of those discs. The radius is the square root of the sine of x. That means our cross-sectional area, we'll call it capital A, equals a circular area, so a pi r squared, but in for r, we're going to put square root of sine of x squared. Another case where we're kind of lucky that the square and the square root are going to cancel, and we can use the expression for area, pi times the sine of x. Okay, so here's your setup. Let's go back and integrate the area to get volume. Volume of the shape in question is going to equal the integral from one x value to another from 0 to pi as presented in the question of the area, which we were talking about here, pi times the sine of x taken with respect to x. And now it's time to integrate. Leave the pi completely outside of the process and integrate the sine of x. Think of a function that would have sine as its derivative, and that would be negative cosine of x. Evaluate it from 0 to pi. Next step is the plug-in. I'm going to pull the negative to the outside, and I'll just say negative pi times the cosine of the top number, so the cosine of the high limit of integration, pi, minus the cosine of 0 is one way you could show your work. So negative pi times the cosine of pi, which you can find either on a unit circle or a calculator as negative 1, minus the cosine of 0, which is 1. So this is negative pi times negative 2. So no matter how you show your work, again running out of space here, you get 2 pi units cubed. Each of these answers so far I've been answering pretty much always in exact form like this. You could always say 6.28. You could always give me a decimal approximation as well. So for homework, you're going to flip the page to 8 and you're going to try 1, 2, and 3 where you have a little disc graphic at the top. I was just thinking the last thing I would do would be to help you get a head start on that. We can look at number 2 together. Okay, so have this one set up. The last one I didn't show you the demo for, but here's what it would have looked like. So in the last question, we were revolving the sine of x, the square root of the sine of x, around the x-axis, and you get this kind of 3D football shape. Let's see what this one's going to look like, this homework question. And here, for the first time, we are graphing our own 2D version, and then we're graphing our own 3-dimensional version next to it. I know, as well as the next person, that it is tough to make these drawings look really nice. Really just know that you're not going to be judged on the way that your graphs look, how beautiful or accurate they look. These pictures are really just for you to help you visualize the problem on this page. So let's work through 2 together. Let's get a 2D sketch first. Can you start with sketching e to the x? So usually we raise e to a couple easy powers. E to the 0 is 1. E to the first power is 2.71828. So if I'm just going to count by a scale of 1 here, you have this exponential growth curving up to the right. To the left, it's going to get smaller and smaller, but it'll hit an asymptote at 0. It'll actually never hit that value. You'll notice that the directions at the top of the page say find the volume of the solid obtained by rotating the region bounded by the given curve. So bounded by all these curves here are lines, revolved about the coordinate axis that's specified. So we have to revolve this region about the x-axis. Well, here's the graph of e to the x. The graphs of y equals 0 and x equals 0 are actually the x-axis and the y-axis here and here that are already depicted. And the only thing I haven't put on here yet is the line y equals 1. So let's see if I can just sketch a line and I meant to say x equals 1, right? We're going from 0 to 1 on the x-axis. We're going just above the x-axis as well. So let's shade the region in question, and it's going to be this little region here. Okay, and we're about to tackle the tough part. We want to see if we can sketch this in 3D. So we are picturing that we're going to spin this shaded region about the x-axis, revolve it about the x-axis. So my advice is when you're sketching it, it's a little bit easier to sketch in 2D than it is 3D. So here's my advice. Start by sketching the curve that we just got done putting on our graph. So that, for starters, was just the part that was above the x-axis. Because when we spin it, it's going to mirror down below the x-axis, what you'll see is, if you're trying to sketch this for yourself, you'll see a mirror image mirrored across the axis of symmetry, right across the x-axis. What I do in my drawings, because they never look that pretty, but what I do to make them look more three-dimensional is, instead of connecting them with a straight line, I'll connect them with a circle and maybe just part of a circle here. Then what I see, and just bear with me here, it's kind of like a megaphone on its side, like something I could talk through, and you see it looks a little bit more 3D. And what's important is, if this is a rectangle that's getting revolved, it's going to generate a cross section that should be a disc. We should be able to use the disc method for all the examples on this page. You get a circular cross section in the middle there. Again, disclaimer, you don't even have to draw these pictures. These pictures are here for us to be able to visualize the function. All that being said, if you're getting frustrated with the 3D version, take a look at this, because I have a little simulation like I did for the last one. So here's the graph of e to the x, and I want to cut it off. I want to graph it from 0 to 1. I'm going to hit revolve. I'm going to go around the x-axis, and this is a better picture of the shape I was just trying to draw with you. You see it coming around from the outside, and you see, even though it looks hollow, ours is filled in, that megaphone or maybe like a hat sort of shape that you could see there. All right, so let's go back and actually solve the problem. We need the area of a cross section. We need the area of one disc, and that's going to involve a radius value, the height of, just kind of from the x-axis up to the top, which is changing as you go. Again, what would be the height of each of these cross sections as you go across the graph from 0 to 1? The height would be where the disk hits the graph, y equals e to the x. No matter what the x value is in this little range here, the height is going to be e to that number. So let's use r equals e to the x, the original function. So cross-sectional area, we're talking about circular area, should make you think of pi r squared like the last example. Let's use pi e to the x squared. We're using e to the x instead of r. So now I'll go back up and try to finish this one the way that we solved the others. We're going to integrate from one x value to another, so 0 to 1, a pi r squared, but for r, we're using the equation y equals e to the x. So it'll be e to the x squared taken with respect to x. And this is otherwise known as pi e to the 2x dx. The pi isn't going to get in our way too much. The pi is a constant, and it can always be pushed outside of the integral and kind of just applied to our final answer. Our focus right now should be the e to the 2x part. And while we know e to the x is its own antiderivative, which is very convenient, here's a rule that I sometimes use in this case. So the rule is, if you're ever integrating e to the something x, right? You have a coefficient in front of the x, we'll call it e to the kx. You can use 1 over k e to the kx plus c. And I'm going to employ this rule to help simplify what we wrote here for volume. So what does it say? We'll leave the constant in our answer, so we'll write pi. Then next to it, e to the 2x's integral, rule says we'll go 1 over 2 e to the 2x. And instead of a plus c, this is a definite integral, evaluated again from 0 to 1. That seems to be a common interval for some of these questions we've tried. Well, the pi can stay on the outside, and we need to plug in the 1 and follow it up with plugging in the 0. And even the 1/2, that's a constant as well. The half pi can stay on the outside. E to the 2 times 1 minus e to the 2 times 0, which actually doesn't go away in this case. We've got pi over 2, e squared minus 1. And so that is your exact value. You could say pi over 2 e squared minus pi over 2. That seems kind of tricky looking for an exact value. So I would go straight to a calculator, type it in, round the decimal. I think I wrote it to the nearest thousandth. See if you get something around 10.036 units cubed, since this is volume. Another good approximation. All right, it's been a pleasure, and I'll see you next time. Thanks.